and potential energy surfaces, we talked about how transition states are stationary points on the protein potential energy surface landscape. They differ from peaks and valleys in the sense that first derivative is equal to 0 at this point, same as the other points, but at this saddle point, all the second derivatives are positive except the one in the direction of the reaction. So it's downhill in only one direction. So reaction progress is traversing this saddle point from one valley to the other. Your ability to do that is of course going to depend on how high up this saddle point is and also the kinetic energy you have in that valley. And for our purposes, molecular kinetic energy is the same thing as temperature. You increase temperature, you increase kinetic energy. There's a Boltzmann distribution function involved in that, which we won't worry about in any level of detail. One thing to know, however, about this saddle point and your ability to travel from one side to the other is, here's a zoom in on the saddle point in the bold orange line. That is sort of the average path over the saddle point, but you actually have variation around that in terms of the path that's taken over the saddle point. So each individual trajectory of the molecule, of a molecule in a reaction can be a little bit different. What we think of as the reaction coordinate is just the weighted average of the various trajectories over this pathway. And the idea that there's some distribution of geometries at the saddle point, I don't know how to pronounce this, call. I honestly don't even know what that means, but this is the ridge at the saddle point. The distribution of various geometries along this ridge is important and was an important aspect of how Eyring's transition state theory was derived. So we're going to talk about that briefly. We'll talk also about general principles that organic chemists use to understand reaction kinetics, and then we'll move on from there. We'll spend the last part of chapter 7 actually deriving rate laws for various situations. You're going to love it. So reaction kinetics, we typically assess how fast a reaction happens in experiments where we can measure the concentration of some product as a function of time. And usually we'll see something like this where the product concentration increases in a pseudo-linear way, and then depending on the situation sort of levels off. And so this line represents the concentration of your product increasing as a function of time. And we haven't described the reaction at all, and so there could be various ways to think about what's going on here. Typically, we can derive a rate law for a particular reaction where the rate is the change in product as a function of time. So this is actually just the first derivative of product concentration with time. Thanks, that's very soothing. I appreciate that. And then the rate law involves some rate constant, and then you have concentration terms for, say, starting materials. And we're just going to be general here. Concentration of starting material A, and then this exponent represents what we're going to call the molecularity of the reaction in the concentration of A. In other words, how many, or the order is another way, order or molecularity of the reaction in the concentration of A. Or in other words, how many molecules of A are involved in the rate determining transition state. Same thing with B if there's more than one molecule involved. Typically these exponents are low because it's hard to, in organic chemistry or any chemistry. A two-body collision is okay. A three-body collision is almost impossible. Usually what has to happen for that to occur is you have a two-body collision to make a complex, and then a third thing comes along. So we're going to see reactions that, elementary reaction steps that just involve a single step generally have exponents of 1, maybe 2. Okay, so let's talk about this rate constant. Eyring's transition state theory is based on an interesting assumption that you wouldn't think would apply. So for a reaction where A plus B goes to C, Eyring said, okay, the change in concentration of product C as a function of time should equal some rate constant times the concentration of A times the concentration of B. Nothing new there. But then Eyring said, actually, that should also be equal to some rate constant K double dagger, where this is related to a vibration in the what he called the activated complex, or the transition state, a vibration in that transition state that makes it resemble product more, meaning sort of the rate of moving further down the reaction coordinate, and then the concentration of that activated complex. In other words, he said, well, if this is a reaction A to B going to C, you can represent the rate as being rate constant times concentration of A times concentration of B, or you can just say concentration of your activated complex of A and B times some rate constant that tells you what the vibration is that allows you to move toward products. Making sense, sort of, so far? Questions?
This outside the bracket is defined, right?
Huh? Put what outside the bracket? The double dagger. Yeah. You for our purposes, you can put it inside, outside, doesn't matter. Yep, sorry. Okay, so then the important idea was this idea that molecules A and B are in pseudo-equilibrium with the activated complex. And of course, they can't be in real equilibrium because the activated complex is a transition state, not an intermediate. Equilibria involve energy minima, not energy maxima. Nevertheless, the idea that you could think of it as sort of an equilibrium relates to the fact that even at the transition state, there's some Boltzmann-like distribution of geometries. And that was enough to make the postulate useful. And so you can write a transition state equilibrium constant that's just equal to the concentration of the activated complex divided by the concentration of A divided by the concentration of B. And so we could rewrite the rate law using this information. The appearance of product should be related to this vibrational constant little k double dagger, this equilibrium constant big K double dagger, and then the concentrations of A and B. So the key insight here is we're parsing this rate constant into two different contributions. One has to do with vibrational frequency, and the other has to do with how much of that activated complex is formed. Let's see. you can write that equilibrium constant as the Boltzmann constant times temperature times the exponential of minus delta G double dagger, that's the activation energy, over RT. And then there was some terms in the denominator. H is Planck's constant, and then you have some frequency nu, and nu here is the frequency of the vibration that leads you more towards products. Right. And then the other thing was to say that this little k double dagger is also related to that frequency that leads to products times some other constant kappa. Now, just go with it because I realize this is all kind of complicated and I'm not going to ask you to derive anything here. But in general, if you take all that I've shown you, the activation energy for a reaction equals minus RT times the natural log of K times H divided by kappa. How do we even write kappa? I don't know. Times Boltzmann's constant times temperature. So the basic idea here is there is a physical connection between the rate of a reaction and its activation energy, which we sort of expect, and you learn that in general chemistry, but that this activation energy is related to fundamental physical constants and details about the reaction. Real briefly, again, this nu is the frequency of the vibration in the activated complex that leads to product. Product C, and this kappa is what's called a transmission coefficient, and that reflects the fact that when you get to the activated complex, you don't always go forward, sometimes you go backwards. And so all of those factors together you can bring together to get the activation energy, and you can know what various parts that activation energy comes from. All right, that's probably enough for Eyring's transition state theory. Right. One thing you can do with this, if you want to, yes, sorry, go ahead.
Which K is in the denominator there? Because you got kappa H on the top.
Okay.
K Boltzmann, and what's the other K?
Right, I'm sorry. Let's go back. All right. So based on our equation for the rate law, rate constant times the concentration of A times the concentration of B. Rate constant is, we can measure the rate. Rate constant is something we'd like to know and be able to predict. We're relating that to a pseudo-equilibrium constant, which we can actually represent as, Boltzmann's constant times temperature divided by Planck's constant times the frequency of the vibration times the exponential of opposite of activation energy over RT. Sorry, still processing. I hate it when I do this. Sorry, sometimes things are confusing.
So, in that final equation with the delta G, the K on the bottom is K and R, for the one that has a little arrow under it. The K of the reaction.
I erased it, so now I'm having a hard time telling you what. Okay, I'm sorry. Let me just get everything straight. Oh, right. I'm really sorry. Darn it. Oh, okay. So this is also equal to some activated rate constant times the concentration of the activated complex, which, based on this equation here, we can substitute in activated complex rate constant times equilibrium constant times A times B. I'm telling you that the equilibrium activation complex, equilibrium constant for the activated complex is shown here. And then we're saying that little k for the activated complex, the rate constant going from there to there, is equal to that new frequency. And then I'm not sure how to draw the Greek letter kappa. Anybody know?
Just put a K and drew a line over the top, so that I know what the K is.
Okay, sure. This is the transmission coefficient, telling you once you get to the transition state how frequently you go forward versus backwards. Again, nu is the vibration in the activated complex that leads to product. So if we put all of this together, substituting in this for this, and then maybe we want a color other than, and then all of this for K, what we would come up with for the rate equation would be nu times kappa times Boltzmann's constant times temperature divided by h nu times the exponential of minus delta G over RT.
So is that e to the negative delta G over
Yeah,
RT?
yeah, that's.
Okay, it's not on the t's. Got it.
Yeah, exp is a notation for e to the, it's just harder. I do that so that I don't have to write all of this stuff small. Okay. And then the new numbers cancel each other out. And by the way, we still have to put the concentration of A and B there. All right. And what we can conclude then is that the rate constant equals kappa, transmission coefficient, times Boltzmann's constant times temperature divided by h, Planck's constant, times e raised to the minus delta G over RT. So this tells you that the rate constant for the reaction that we can measure is a function of kappa, which is a transmission coefficient, and the activation energy. All right? So that was a lot, and I'm sorry, but this was the connection between rate constant and activation energy for a molecule, for a molecular process. And so what you can do in a reaction is you can measure the rate as a function of concentration. And we'll talk about those experiments later. But you can basically measure a rate constant, right? And if I measure that rate constant, and then I plot it versus the natural log of, well, let me just rearrange things and then I can show you what kind of plot you can use so this is going to be data that we get that's going to give us this K value. If I rearrange some things, rate constant K, which I measure, and then just rearranging things, and then I take the natural log of that, that's going to equal delta G over RT. Or, in other words, minus delta H over RT minus negative T delta S over RT. So if I plot the natural log of this rate constant times these other constants and temperature, if I plot that versus 1 over T, the slope of that is going to be opposite of delta H activation for the activation enthalpy. Heavy sighs, I'm sorry. And then the intercept is going to be the activation entropy. So in a plot of natural log of the rate constant, and again, this is not so you can do any calculations directly, it's so you can understand what people are doing in papers that you read. If you plot this versus 1 over T, you're going to get perhaps some, and with 1 over T, this is high temperature to low temperature. You're going to get a line that looks like perhaps this, and the slope of that line is going to tell you something about the activation enthalpy. And remember, activation enthalpy is always about interactions formed versus interactions broken. And then the intercept is going to tell you about the change in entropy for a reaction, the activation entropy. So here's an example plot. Here, the reaction make sure I don't get this wrong. So in this particular example, they use light to extrude a carbene from this system, generating this anthracene and then this carbene. And from that carbene, you can get two different products. And you can compare the relative rates of those two products that lead to 4 and 3, rate constant A and rate constant R. And if you take the natural log of that ratio, the slope here is going to tell you something about the change in enthalpy to get to the activation state. But now, because you're looking at relative rates, this is going to tell you the difference in the enthalpy of activation between these two pathways. And so you can tell if going from this common set of intermediates to these two products, you can sort of tell, is the difference in rate between these two because of enthalpy mostly, or is it because of entropy? And that can be useful to know. Another example, this was rate constant data with these other constants for an enzyme whose reaction is not particularly important for us to worry about. But if you plot the rate of the reaction versus 1 over t, you see a certain slope in this region, and this region is high temperature. And then you see a different slope in this lower temperature region. And remember that slope is going to be opposite of activation enthalpy over R. So both slopes are negative, but which one has a higher magnitude? To the right, right? So this is going to have higher enthalpy of activation versus lower enthalpy of activation. And it's thought that the reason this activation enthalpy is higher at lower temperature is because before 31 or 32 degrees, the protein enzyme actually has to change its conformation to get to an active form. But that after 32 degrees C, the protein is already in its active form, and so the activation enthalpy goes down. This can be useful because the fact that it changes tells you something about what's going on in the reaction. A change in the slope is related to a change in the mechanism. Okay, so let's see, there's, yes, go ahead. Where are the kappa terms?
Yeah.
It's possible that you're just assuming kappa's 1, depending on the reaction. That's a good question. I'm sorry I don't have a better answer to that. Yeah. All right, I want to make sure I'm not missing anything from my various notes. The other thing you're going to see is the Arrhenius relationship, which we can summarize real briefly. The Arrhenius relationship is for macroscopic processes, but the form of it is basically similar. This is perhaps what you've seen. Rate constant equals some prefactor times the exponential of the opposite of activation energy over RT. So we're not necessarily parsing this into entropy and enthalpy components, and we're also, this can work for processes that aren't involving single molecules. So for example, I remember learning years ago, and I think you can look this up, if you measure the rate for a process, for example, students taking an exam or solving a problem, and then you do that at various temperatures, seems terrible, right? And you plot the natural log of the rate that you observe versus the natural log of A plus minus EA over RT. So if you plot that rate constant natural log versus 1 over T, you're also going to get an activation energy. And that's the activation energy of what? Thought or something like that. But you can actually do that, and it's been years since I saw this, so I don't know how accurate it is. But you know, the numbers they were drawing out of this were somewhat related to the activation energy of ATP hydrolysis or something like that. We can look it up. I'll see if I could find it and send that to you.
Did they actually torture their students like that?
Yeah, I'm not sure. There are a lot of things that people did previously that probably wouldn't pass IRB approval for human subjects research, but.
But I think even if you don't have to engage the student in that kind of different temperature, different countries in the world learning at different temperatures is already something like that. How we learn in Africa and how you learn in this.
Oh, that's interesting, yeah.
More colder. It's warm in Africa.
Yeah.
And yeah, it's cold now in the US. So it's already like, okay, and they learn in Africa. And they learn.
That's true.
At different temperature.
Yep. Aside from the fact that if I'm sweating profusely and it's dripping in my eyes, I get angry, and then when I'm angry, I'm not learning very well. So there's complicating factors there for sure.
Like the freezing and shivering.
Freezing and shivering too, yeah, totally.
That cold here.
There are always, learning is,
You know what?
I'm from Minnesota. It's not that cold here.
Okay. Nice.
there is I forget what it's called. There's a movie from several years back called New in Town about a corporate executive that comes to shut down a plant in Minnesota, and she ends up stuck because of the weather. But you know, she just gets off the plane and she's dressed kind of like you or I would be right now, and she walks out of the airport, and you can just see as the wind gusts in, she's like, and you don't understand it if you haven't actually experienced it, but that transition in temperature literally makes every part of your body go, and it's quite painful. So anyway, here are some examples. We talked about activation enthalpy. Entropy you can also get from this Eyring type analysis. This kind of plot you will hear people call an Eyring plot. That's the most likely thing you're going to encounter as you read the literature. People will talk about Eyring plots and just understand they're talking about rate constant versus 1 over t. Here are some actual measured entropies. They're in entropy units. Those are annoying, but these are units of calories per mole per Kelvin. But we don't care about their absolute values, just the relative ones. And here are activation entropies for various famous reactions. Acid catalyzed ester hydrolysis in water, entropy of activation is pretty high. You lose 26 entropy units. Entropy goes down. That makes sense because the transition state involves two molecules coming together. It's not quite so bad for acid catalyzed ring opening of ethylene oxide in water, epoxide opening. But you've been told that epoxide opening is, in acidic conditions, is SN1-like, meaning that the leaving group has already left a lot before the nucleophile comes in, and so maybe the nucleophile doesn't have to be very close before the rate determining step happens. For this reaction where you're hydrolyzing pyranoside or an acetal, you're splitting one thing into two, and so now entropy of activation is positive in a favorable direction. And for, you can measure rates of solvolysis of T-butyl chloride, and again, one thing going to two, that's in a favorable direction. Homolysis, so basically your intuition is pretty good here in terms of what you expect activation entropy to be when you actually go and measure it. All right, so with all of that, let's now, and that's really just to give you the background to understand stuff when you read it in the literature. Let's now talk about rules of thumb that organic chemists use all the time. So one is the Hammond postulate, and this actually showed up on your previous exam, so we hadn't talked about it, but you had to go look it up. What is the Hammond postulate?
Except that when you have your like
So that principle is a true principle, but that is called, I think, the Aufbau principle. German word for I don't know what. Hammond postulate is the idea that if you're in a situation like this where you have starting material and products, the transition state resembles whichever adjacent state to which it is closest in energy. So, for example, in this situation where the starting material and the transition state are relatively close in energy, whereas the product is further away in energy, we're going to say that the transition state resembles the starting material. People will sometimes call this an early transition state because geometrically the transition state is closer to the starting material, meaning you have to change less to get from here to here. Because remember, along this x-axis, the y-axis is of course energy, and the x-axis we've called reaction coordinate, but it is really some kind of geometry change in the molecule, right? So the idea is if you don't have to change energy very much to go from one state to an adjacent state, you must also not have to change geometry very much. And so, the application of this is we use things that we know about stability of starting materials to rationalize things about the transition state, which we can't directly observe. Similarly, if the transition state were close to products, you would say starting material is here, here's the transition state, and here is the products. You would say that the transition state resembles product geometry. And we might call this a late transition state because the transition state, the geometry has to get nearly to product before you get to the transition state. A classic example of this situation is solvolysis of T-butyl chloride to give a carbocationic intermediate. The rate of a so-called SN1 reaction, we've said, is higher for tertiary alkyl halides than secondary or primary. We've rationalized that because primary carbocations are less stable than secondary, which are less stable than tertiary. But the stability of an intermediate may not necessarily tell you anything about the kinetics of the reaction. The reason that works here is because this step of the reaction is uphill in energy. It's endothermic, so the transition state and the product are closer in energy than the transition state and the starting material. So the transition state is carbocation-like, meaning what stabilizes the carbocation will also stabilize the transition state. That's the reasoning that we use. Sometimes, so it's not any more complicated than that, but sometimes people will make it worse by saying, well, for exothermic reactions, you generally have an early transition state. Don't memorize that. This is an exothermic reaction, but the reason it has an early transition state is because the starting material is closer to the transition state. Yep. People will also say, oh, endothermic reactions have late transition state. And again, you can memorize that if you want, but you don't need to if you understand the idea that two adjacent states in an energy diagram that are close in energy must necessarily be close in geometry. All right. Hammond postulate.
Can you give an example of the LA transition state reaction?
A reaction of, I'm sorry, an example of what?
The LA transition state reaction. An example, just like we give this for this late transition state.
Late transition state.
Do you give an example?
Yeah, this is an example of a late transition
Can
state.
you give an example of the early?
Early transition state, sure. Let me think. um, off the top of my head. Early transition state. Dang it.
Does it have anything to do with the kind of carbocation that will be formed?
Well, carbocation formation is always uphill in energy. So to go from something that's neutral to something that's carbocation-like, to go from a starting material to a product that's downhill in energy. So suppose this, I mean, because this is just a single step reaction, let's try the SN2 reaction as an example. And I don't actually have energies calculated for this, so what I'm going to tell you the specific example I'm going to give you may or may not reflect reality. But let's imagine that we're using methyl iodide and then some really good strong nucleophile like ethane thiolate. And of course, we're going to draw the SN2 reaction like this, and it's very downhill in energy. That would suggest that the starting material, if we were to draw the transition state for this SN2 reaction, you've typically drawn SN2 transition states like this, with the leaving group here and the nucleophile here. The degree to be early versus late would just be which bond is broken earlier versus which bond is broken later. So if this is starting material, an early transition state would look like this. The bond between, the breaking bond between carbon and iodide would be, again, we're going to resemble starting material, so that bond is going to be shorter than the incoming bond between our nucleophile, whatever it is, and there should be more negative charge here, less negative charge there, and you would predict the hydrogens would be not perfectly planar. So we'd have to do the calculations to figure that out, but that's what an early transition state would look like.
So there's no carbocation in the early transition state?
Well, because this is an SN2 reaction, early versus late transition state you can apply to various mechanisms. So it doesn't have anything to do per se to a carbocation. The reason the carbocation goes through a late transition state is simply because carbocation formation is uphill in energy. And so the transition state will have to be closer to the carbocation than it is to the starting material. But there are other reactions that would be this way too, just as there would be other reactions that are this way. All right. Dang, that's it. We were going to do next the reactivity selectivity principle. It's kind of, that principle is kind of like the pirate code. It is more guidelines than actual rules, and there's a lot of exceptions to it. So it may or may not be useful to you. I'll show you one example where it is, but we'll save all of that for Monday. All right, so my assignments are, what am I supposed to do? I'm supposed to post Prob Practice Exam 2 solutions, and I'm also supposed to send you the thought rate versus temperature paper to see what the activation energy of thought is. What's that? Your exams are now posted. The exam 2 is posted on Learning Suite now. Yep. You can feel free, it's in Word format, so you can feel free to type your answers to the extent that you need to write stuff. You can also print it out and write. If you want to use ChemDraw to draw structures, that's fine. If you want to do it by hand, that's fine, whatever you want.
You know, Price, you said you're going to post it yesterday to give an extra date. Now you're posting it today.
Right, so Tuesday. Yeah, I am sorry.
It's all
Please,
good.
Bryce.
You're all good, it's fine.
Yep.
Yesterday.